Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to continue with shear and bending moment diagrams using just kind of relationships and basically trying to avoid equations at all costs. Now, in the previous example, we covered point loads and concentrated moments, so that's kind of the nice and easy one. But now we're going to make things a little bit trickier by introducing a constant distributed load. So as I told you guys in the last video, this constant distributed load is actually not too bad. And using these relationships, we'll be able to solve for the whole diagram probably pretty quickly. Now, there's going to be a couple extra tricks involved, and I'm going to show you those because those are the tricks they love to throw at the final. And again, even though this is getting a little bit worse, not too bad. Now, if this distributed load became linear, we're going to have to start a lot of problems. But I'll show you guys that in the next video because that's usually a final exam question. A linear distributed load, because things get really, really messy. But let's just forget about it for now. We have to acknowledge that we're still in the nice easy part. So just sit back, relax, and enjoy. And let's get started. Alrighty, so looking at this example, it wants us to draw the shear and moment diagrams for the beam. So exact same question as we had last time, and probably the exact same question that you will get on your final. So we're just going to kind of jump into it real quick. First thing that we'll always need to do for these type of problems, we're going to have to find support reactions. Support reactions. So if you're ever finding support reactions, we will check if you draw a free body diagram of the beam. So I highly recommend that you guys get used to drawing free body diagrams because, yes, they're going to be very important. And I think some of you got some marks off on your midterm for not drawing free body diagrams. So let that be a little bit of a warning to you. So here's my beam. I know at A, it's a pin, so I'm going to have AX and AY. So there's my AY, and I'm just going to go to the other side and draw BY, because it's a roller. So we got AX, or AY, sorry, and BY. I have AX, which is going to be coming across, but again, as you guys will see, AX is going to be nothing. Very rare that beams have any of those lateral loads. So at the end of the beam, I have a concentrated load and a concentrated moment. But I know at this point you guys are just laughing because if you guys watched the last video, you guys are going to know exactly what these do to the beam. So these aren't too scary. And we have 150 kilonewton meters. But what's going to start to scare you guys now is we have a distributed load. Oops, that didn't work out too well. So we have a distributed load, comes across like this. We know that the magnitude of it is going to be 40 kilonewtons per meter, and this will result in a kind of a force at the center like this, and I'm just going to call this force right now F1. Finally, I'm just going to dimension our beam real quick, so it's actually really nice and easy dimensions, even though this is horribly to scale, so not even close. We got 8 meters and we have 3 meters. Alrighty, so from here we can start to calculate everything. First thing I'm going to do is just find out F1 real quick because we're going to need it for our calculation. So we're going to have 40 kilonewtons per meter times a distance of 8 meters. And if I grab my calculator, I get 320 kilonewtons. So quite a hefty load actually on this beam. Starting with some of the forces in X because it's going to be very, very trivial. We go sum of the forces in X equal to 0. And what we get is AX is equal to 0 kilonewtons. So that one's always nice and easy. Like I said, very rare that you get a beam with a lateral load. The only exception is when they give you diagonal beams, but that's a very special case, and we'll talk about that. We'll talk about that a little bit later because that's usually a good one to try and mess you guys up really bad. All right. So what we can also do is we can take the sum of the moments about A, so about the pin, is equal to 0. So by doing that, I'm going to get a long equation. I got F1, which we now know is 320. And it's going to act at a distance of 4 meters. And it's going to create a negative moment. We're going to have BY, which is going to create a positive moment, acting at a distance of 8 meters. Then at the far end of the beam, we have 20 kilonewtons going down. So we're going to have minus 20. And this is going to be at a distance of 11 meters. And finally, we have 150 kilonewton meters, and we can see that this one's going clockwise, so it's going to be minus 150, and all that is equal to 0. So We can easily solve this, and what we find is that our By is going to be equal to 206 kilonewtons. Had some decimals, but we're just going to get rid of the decimals. And again, I like to highlight this because we will need this in our moment diagram. So 206 kilonewtons. So now that we found that one, it's very easy to find AY, because if we go sum of the forces and Y is equal to 0, we'll have AY going upwards, and then we'll have minus F1 and the 20. So minus 320, and then minus 20. And then we have plus By, so plus 206 is equal to 0. So solving that, we can easily find that AY is going to be equal to 134 kilonewtons. So it's also good to note that AY and BY both go up. So I'm just going to throw that real quick up here because we will need those directions a little bit later on. So first step is always finding support reactions. And when you're finding those support reactions, please, please, please draw a free body diagram. You'll get lots of marks off. It's a very important concept in this course. So please draw a free body diagram. But now we're going to get into the fun part, which is the shear and bending moment diagram. So like I said before, the first thing that we're going to want to do is we're going to want to draw the beam again with all the loads on it. So no unknowns, just all the loads. So I'm going to come down here and I'm going to try and draw this one a little bit more to scale, a little bit more at least. So we're going to have 3 meters and then we're going to have 2, 4, 6, 8. So that was pretty painful to watch me drag out, but it's going to be more to scale now, which is hopefully what we want. So we're going to have a beam. If we're looking at the loads that we have on it, well, we know that AY is going to act right here, and we have BY acting over here. So our AY is 134 kilonewtons, and BY is 206 kilonewtons. At the end of the beam, we have a point load of 20 kilonewtons, and then we have a distributed load across the 8 meters of that beam. So I'm just going to draw, a distributed load of 8 meters, or over a span of 8 meters, and this load has a magnitude of 40 kilonewtons per meter. So one thing that you guys will see me not draw is actually the value of F1, because for these diagrams we do not take it as a singular force. The only time we convert a distributed load into a single force is when we're solving for those support reactions, or if we're solving for the internal forces at a point. But for the moment diagram throughout the beam, we're actually not going to need it. So finally, we can't forget about our concentrated moments of 150 kilonewton meters on that side. So again, we're going to just dimension the beam like this. So we know that we have one span of 8 meters and a second span of 3 meters. At 8 meters, and we got 3 meters. So like I did before, I'm going to start drawing vertical lines where my spans are. So the first one's the 8 meters, so I'm going to draw this. Oops. So like this is going to be our first span. This is going to be our second span. And at the end, this is where the beam ends. So something like that. And I'm going to draw where my shear and bending moment diagram will be. So let's do the shear diagram right here. So this will be when the shear is equal to 0. And then we'll go down here a bit more and we'll find out, and we'll not find out, but we'll draw, we'll give it a bit more space. We'll go right here. And this right here will be when the bending moment is equal to 0. So I'm just going to label these really quick. So the first one is going to be our shear diagram. And this will have units of kilonewtons. And then our second diagram, as we said, is bending moment. So I'm going to put, I was going to put bending moment, and you should put bending moment, but it's okay if you just put moment. And this will be kilonewton meters. So now we got to figure out what to do. So it's the same procedure as before, where we want to go from left to right, and every time there's a jump or a concentrated load or a concentrated moment, we're going to make the necessary jumps. So if we look at this right away, I start my shear at 0, so just like before, and the first thing I see is I have a concentrated load of 134 kilonewtons. Okay, so what's going to happen is I'm going to jump up to 134 kilonewtons. So that's the exact same as before, concentrated loads. They'll jump up my shear, or they'll jump up my shear diagram. But now this is when it kind of gets tricky, because now we have a distributed load, and we know that that's going to affect our shear diagram somehow. And it's kind of the exact same as what we did before, how it defined the change in moment between 2 points. We took the area of the shear diagram. Well, now define the change in shear between 2 points. So we want to find the change in shear between x equals 0 and x equals 8. We're going to take the area of the load. So I'm going to come down here and I'm going to write these in blue so that for the shear diagram, and hopefully this will make more sense, the change in shear from 0 to 8, so x equals 0 to 8, is equal to the area, I guess I'll just put area of distributed load. Okay, well, we can figure that out because if we look up, our distributed load is 40 kilonewton per meter high and 8 meters long, and it's just a square. So it's going to be 40 times 8. And we already did this calculation. What we found is that that is equal to 320. So here's kind of a little trick, is when you guys take the area, you guys put 40 and 8. And that gives you an answer of positive 320. So a lot of people will go, okay, we're going to go up like this by a factor of 320. Well, that's actually incorrect. And the problem with that is if we look at that distributed load, even though we don't show it, but I'll show it a little bit more clear now, this distributed load actually acts downwards. So if we were technically being proper and correct, what we would do in our calculations is coming down here, we should have, and I'm going to switch colors, negative 40, and our answer is negative 320. So in our diagram, what we find is we go from 134 and we're going to have to subtract 320. And what that does is that brings us to a value of negative 186. So somewhere down here we're going to go negative 1, oops, change color, negative 186. So we know that our shear at that point x equals 9, is going to be at negative 186. And now this comes back to what we discussed about moment before. If our shear is constant, our moment is linear. And this relationship is actually going to be the same between shear and load. If our distributed load is constant, which it is constant, our shear is going to be linear. So something like this. And this is very, very, very important. And the reason why this is will be discussed in the next video, because we're going to get into the proofs of this. But I don't want to always show you guys the proofs because, let's be honest, you guys don't care. All you guys need to know is if that's constant, that's linear. You guys don't need to know the proofs or anything like that. So if that's the case, we know our shear diagram is going to look like this. And at the end of the distributed load, what we see is we have a concentrated force of 206. So what's going to happen is our load's going to jump up by 206. So something like this. And that'll leave us at positive 20. Between the next 2 points, absolutely nothing happens. And then at the very end, we have a 20 kilonewton force going downwards, which is perfect because that brings us back to 0. So our shear diagram is going to be the following. So as you guys can see, not too bad at all. I'm just going to draw this quicker. It's pretty cringy when I'm trying to make all the lines straight. So this will be our shear diagram right here. And we have all the values on it, so it's great. And it's just the same as what we did between moment and shear before. If we have a distributed load, to find the change in the shear between 2 points, we just take the area of that distributed load. So it's great. And we come down, well, we can start moment now. So for moment, what we do is we start at 0, just like shear. And to find the change in moment between 2 points, we need to find the area under the curve. So if we come up here, to find the change in shear, the change in moments, we're going to need to find the area under this curve. Well, we know that that's easy because it's a triangle. So it's going to be base. Oh, now we see a problem. We don't know where exactly the base of this triangle is. So it's a big problem. I'm going to put it in pink. If we need to find the area of the shear, we're going to need this distance, which I'll call x. We don't know what x is. So this is actually going to be a big problem. So before we can actually determine the moment diagram, we're going to need to find where the shear diagram intercepts the x-axis. Or in this case, when the shear is equal to 0. And what you guys will find is, even though you guys don't like doing this, you're going to kind of have to. Because what you'll see is this location here, where the shear is equal to 0, it's going to be a very special point on our moment diagram. So to find that, there's actually a very special method. And I'm going to put this. So for a shear diagram, I'm going to put the root, because that's what we're trying to find, is when it's equal to 0. We know that the change in shear between 0 and then to point x, because we don't know what x is going to be equal to 134 newtons. We want the change in shear from here to here. So this delta V is equal to 134. Okay, well that's not bad. So our change in shear, remember, is the area, is equal to 134. And this is going to be equal to the area under the distributed load. So if I were to take my pink again, and I go all the way up here, all the way up to the distributed load, I'm going to want this area right here. So I'm going to kind of highlight in pink. So this area we know is going to be base times height. And the height is going to be 40, and we know that the base of it, so from here to here, well, we know that that's x, because that's what we're trying to find. So we're coming down to here, we're going to say that we know the change in shear is going to be 134, which is equal to the area, which is going to be 40 times x. So we can actually solve this equation for x and find out that x is equal to, I'm just going to grab my calculator, 3.35 meters. 3.35 meters. So I can come up here, and on my diagram, and this is going to be very, very important, guys, is that you guys need to say, oh, I'm going to draw this in purple, that this point right here, x, is equal to 3.35 meters. And the question won't say when is the shear equals to 0. That's not the question they're going to ask. That's going to require you. It's going to actually be when is our moment a maximum. So you guys will see that this 3.35 meters is going to be very important. So I'm going to come down here, and we just did everything for a shear diagram. So if we look at our shear, we know the intercept, we know where all the points are, we know the magnitudes. Shear is good. So if we come down here, we can start talking about the moment diagram. And remember what I said, that the change in moment, so delta M from 0, and then we're going to go to where x is, so the 3.35, that's going to be the area of the shear diagram. I know it must be really boring watching me write. So we know that the area under that shear diagram is going to be a triangle, so we're going to have 1/2 of the base, which we now know is 3.35, times the height, which we know is 134. And what happens when you guys throw all this in, you guys will get the answer of 224. So we know, if looking at our moment diagram, if I were to carry this 3.35 meter line down, so this is going to come all the way down. So, because this is where we found the moment at. We know that our moment at this point is going to be somewhere up here at 224. So we're going to have 224. But now here's the problem. We knew that when something was constant, then the next one would be linear. So we had a constant distributed load, we had a linear shear. And just by intuition, you guys are going to tell, well, if we have a linear shear, we're going to have a quadratic moment. And that makes sense because as you guys will see, every time we go down from moment to shear to, from load to shear to moment, we're going to increase by an order. And again, I'll show you why this is next video, because next video we're going to get really into depth on why this is, and it's going to scare you, but it's actually very, very easy. So we know that this is going to be a parabola, and that's fine. But the only problem with it is a parabola can go two ways. Looking at this, it can go this way, or it can go that way. Excuse me. So both of those are parabolas, but we don't know which way it goes. And this is how you guys are going to tell. And this is going to be a little trick. So I'm going to say this out loud, and I want you guys to remember this. If you have paper, write this down. The slope of the moment. So the slope of this diagram down here. Oops. I can't believe I picked green when... Let's go to a fun color. So the slope of this diagram down here, that is equal to the value of shear at that point. So I'll say that again. The slope of the moment diagram is going to be equal to the value of shear at that point. So if I erase this real quick, and I look at x equals 0, so at my point x equals 0, I have a shear of 134 kilonewtons. So what that means is the slope at this point is going to be positive. It's positive 134. I don't need to make it exact, I just need to know it's a positive slope. And if I look at my next point, which is x equals 3.35, I know that my shear at that point is 0. So my slope at this point is 0. So the only way that this diagram is going to work, and I'll just go back to the purple, is if my my moment does something like that. So that's how you tell the correct possible way of your moment diagram, is you look at the values of shear to find your slope. And we'll do this again in the next one so you guys can see. So far we found the moment between x equals 3.35. Now we're going to find the moment under, and I'll just go to my highlighter, the moment caused by this area right here. So we're going to find the value of moment at x equals 8. So coming down here, I'm just going to switch our delta m, oops, write everything in highlighter, really confuse everybody. Our delta m from 3.35 to 8 is going to be the area under that triangle, so it's going to be 1/2 of the base, which we know is 8 minus 3.35 times the height. So the height of this triangle is negative 186. So I'm going to have negative 186. And what I'll find here by throwing this on my calculator, so 0.5 times 8 minus 3.35 times negative 186 is I get a value of negative 432. So I know that my moment at x equals 8 is going to have a value of negative 210, because it's going to drop by negative 432. So we're going to have negative 210. Again, our shear between those 2 points is linear, so we know that our moment is going to be, our moment is going to be parabolic. And the way do we find that? What's the best way to find that? Well, I'll just go orange. I know that my slope at x equals 3.35 is going to be 0. We just talked about that. If I look at the slope at x equals 8, I have to look at my shear at that point. So my shear at x equals 8 is negative 186. So I know at this point I'm going to have a negative slope. So therefore my moment diagram, oops, that looked terrible. Let's see how long it takes me to draw a nice one. All right, so that wasn't too bad. So our moment diagram is going to look something like this between those 2 points. And this is why this is very, very important. Because one of the questions they love to throw on the final, and I almost guarantee you'll see it. What is the maximum positive moment? Well, the maximum positive moment in this diagram is going to be this right here, negative 224. Why is that so hard to find? Well, in order to find that, I needed to find this point right here. I need to change this up. All right, this color. I need to find this point over here. So that's going to be kind of your hint. The location of maximum moment occurs when the shear is equal to 0. So the shear is equal to 0. Oops, I went to the eraser. At my point shear is equal to 0, I see that I have a maximum moment right there. But if I look up at my shear diagram again, there's another point where it equals 0. So let's just find out what happens at that point. So I know my bending moment, I'm going to want to find it now between x equals 8 and x equals 11. So that 3 meter span. So I don't know which color I'm using. Oh, green. So the delta M between 8 to 11 is going to be that area again. So I look up at my shear. And at this time, it's just a nice rectangle. So it's going to be 20 times 3. 20 times 3. So we know that this is going to be 60. Oops, not 6. 6D. So when we come up here, we see that this is going to jump up from negative 210 to 150, or negative 150. So it's going to jump up to this point here. And since the shear is constant, we know that the moment diagram is going to be linear. So we look at that point at x equals 0 again, we see that there's actually another maximum, or relative maximum, and that's at that point. So that if that's the case and they ask for the maximum shear, you guys are going to have to look for the keywords maximum positive shear or maximum negative shear. And sometimes they might just say the absolute value of shear. So if that was the case, well, we know that 220, oops, always went to the eraser again. 224 is greater than 210, so the 224 would be my answer. So to finish this off, our moment's not at 0. We know that maybe something's wrong, but if we look up here, we have a negative concentrated moment at the end of the beam of 150. So a negative moment is going to pop our diagram up, which makes sense because we're at negative 150. And if we go up by 150, we end up back at 0, which is what we want. So this is good. I can start filling in all my fancy lines. And we know that this is going to be the bending moment for this part right here. So as you guys seen in this example, this wasn't too bad. We were able to solve for everything, including the maximum moment, which is right here. We're able to find out when our shear is 0 right there, and we're able to complete the diagrams and have all the values in the end. So kind of the conclusion here, a constant distributed load, it's a little bit more tricky, but it's not super terrible. What you guys will find in the next video is when we have a linear distributed load, things start to get a little bit messed up. And the reason why, excuse me, my voice is getting a little dry now, as you guys can tell. If I have a linear distributed load, my shear is going to be parabolic. Remember, everything's always going to be that one order extra. And if my shear is parabolic, it's going to be real hard to find the area under that curve. And if I can't find the area under my shear curve, how am I supposed to find my change in moment? Because remember, if we look down here, our change in moment is equal to the area under the shear diagram. And if the shear diagram is parabolic, we can't find that area. So that's the only trick where things get really messy. So there's actually two options to figure that out, which we'll discuss in the next video. And one of them is equations, which we did in video 1. And as you guys know, those suck. No one wants to do those equations. But there's actually kind of a secret way that involves the equations, but we can find the equations really fast. We don't have to cut the beam and stuff like that. So we're going to do that way, where we can find those equations without cutting the beam. It's based on relationships and a little bit of calculus. I know you guys aren't the biggest fans of calculus, but you'll be fine. Trust me. If I can do it, you can do it. But I'm not going to talk about it too much. I'm just going to save it for the next video. So thank you guys all so much for listening, and I'll see you guys in the next video.